We're seeing strong secondary enrichment right along this fault line.
Confirmed. The handheld XRF correlates perfectly.
Move it slowly to the mark.
We are aligned on the grid point. Lock the hydraulics.
Blast hole drilling creates precise, deep holes in ore bodies, preparing controlled fractures for efficient copper extraction. Explosive charges are carefully placed in drill holes to fracture ore bodies through controlled detonation patterns. Controlled blasting uses timed detonations to break ore bodies into manageable fragments for efficient material extraction.
After blasting, ore bodies break into fragments of varying size, enabling mechanical handling and transport efficiency.
Hydraulic excavators load fragmented ore into haul trucks for efficient transport from mining benches to processing areas. Haul trucks transport large volumes of copper ore from extraction zones to processing facilities for further reduction. Ore is delivered to primary crushers, where large rocks are reduced in size for further processing stages. Primary crushers apply high mechanical force to reduce large ore rocks into smaller, transportable fragments.
The flow rate on line 3 is spiking again.
Adjust the feeder speed and monitor the distribution.
Conveyor systems transport processed ore continuously between stages, ensuring efficient and uninterrupted material flow. Fine crushing reduces ore into smaller particles, improving surface area for efficient mineral separation in later stages. Grinding circuits reduce ore particles to fine slurry, enabling efficient mineral separation through controlled particle size distribution. Ground ore is mixed with water to form slurry, enabling efficient transport and preparation for mineral separation processes. Chemical reagents are added to slurry to selectively bind copper minerals, enabling efficient separation during flotation. Fine air bubbles form within slurry, providing surfaces for copper minerals to attach during flotation separation. Mineral-laden bubbles form a froth layer, concentrating copper at the surface for collection. Thickening removes excess water, increasing concentrate density before further thermal processing stages. Froth-containing copper concentrate is collected from the surface for further processing and purification. Drying removes residual moisture, producing fine copper concentrate, ready for high-temperature smelting. Copper concentrate is continuously fed into high-temperature furnaces for smelting and metal extraction. At extreme temperatures, copper concentrate undergoes smelting, separating molten metal from unwanted materials. During smelting, copper-rich matte separates from slag due to density differences in molten materials.
Slag is separated and removed from the furnace, allowing copper-rich matte to proceed to further refining stages.
Molten copper matte is carefully transferred in heat-resistant ladles for controlled refining in the next stage. Furnace tapping releases molten copper-rich material through controlled outlets for further refining and purification.
Flow rate is stable, ready for extraction.
Confirmed. Crane moving in the pot clear.
Burner sequence complete. We are holding steady on the soak cycle.
Confirmed. Thermal gradient looks good across all ladles.
Iron impurities oxidize and form slag, which separates and rises above the molten copper for removal.
Blister copper forms as impurities are removed. leaving molten metal with high copper concentration.
Molten blister copper is charged into converters for final refining and impurity removal stages.
Air blowing accelerates oxidation, removing remaining impurities and refining molten copper to higher purity.
Slag composition is stabilizing, but the thickness is increasing.
Adjusting airflow now. Temperature holding steady at 1200.
Final purification refines molten copper, reducing remaining impurities and stabilizing the chemical composition.
We are maintaining the target temperature perfectly.
All systems green. The melt is uniform.
Refined molten copper is carefully transferred to casting systems under controlled high-temperature conditions. Molten copper is positioned for casting into anodes under precise temperature and alignment control.
We are seeing perfect uniformity on the fill levels across the grid.
Excellent. Maintain the current rate.
Freshly cast copper anodes are carefully placed for controlled cooling and structural stabilization.
Check the spacing on the far end. Are we within tolerance?
Yes, the automated frames are holding steady. Electrical connectivity confirmed.
Copper ions dissolve from the anode into the electrolyte under controlled electrical conditions. Copper ions are deposited onto cathodes, forming high-purity metallic layers through electrolysis. Impurities separate and settle as anode sludge, while pure copper continues to deposit on cathodes.
Inside the electrorefining tank system, the accumulated anode sludge, often called slime, is carefully collected from the bottom recovery zones.
Copper cathodes steadily grow as pure ions deposit uniformly during electrorefining.
The impurity levels are consistently dropping across the board. We are maintaining perfect alignment.
High-purity copper cathodes are carefully removed from electrolyte tanks after electrorefining completion.
Cathodes are thoroughly washed to remove electrolyte residues and ensure surface purity.
Cathodes are dried under controlled airflow to remove moisture and prepare for final inspection.
Each copper cathode undergoes strict quality inspection to confirm purity, conductivity, and structural accuracy. Copper reaches 99.99% purity, meeting industrial standards for high-performance electrical and industrial applications.
Refined copper is melted under controlled conditions to prepare it for continuous casting processes.
Forming rollers shape cast copper into rods while preserving internal structure and conductivity. Rolling refines copper dimensions and enhances mechanical properties through controlled compression. Wire drawing reduces copper diameter while maintaining strength and conductivity for electrical applications. Rolling processes transform copper into flat sheets with precise thickness and uniform surface quality. Copper is wound into coils under controlled tension to maintain structure and surface quality. Surface finishing enhances copper quality by removing imperfections and improving reflectivity and durability. Final inspection verifies copper products meet strict industrial standards for quality, accuracy, and performance. Finished copper products are packaged, labeled, and distributed worldwide for industrial and electrical applications.